Hello, hello. I'm here with Falk Amelung, Professor Falk Amelung from Miami University, the Rosenstiel School of Geosciences. Did I get this right, Falk?
Yes, but it's University of Miami. There's also a Miami University.
Oh, I had no idea. I'm so sorry. It's the other way around, obviously. So, yeah, anyway, thanks, Falk, for agreeing to have a little chat with me. And I'm particularly interested in this methodology you're using, InSAR. And I was hoping you can tell me a little bit more about that. I'm a petrologist, so these remote sensing things, they're like magic to me. And I was hoping you can enlighten me a little bit. What's the story with it? How does it work?
Yeah, so we have our satellites flying around at around 700 kilometer elevation at a speed of 7,500 meters per second, so it's pretty fast. They are orbiting the Earth. And then they are taking an image from every, so they're coming back to the same location and taking, every time they come to that location, an image from the same place on Earth, for example, a volcano. And then after a while we're getting time series, maybe 50, 100 images. So now the latest satellites, they take something, they take an image every 6 days. And then we get some good time series, we can combine this, and then we can measure the ground deformation. The trick of this technique is it's a radar, synthetic aperture radar, which works at any, it works in the night, it goes through clouds, so it is, the difference to other remote sensing methods is that the others are mostly optical methods, which just take photographs essentially, but we are sending a signal and that comes back.
I see, that's the trick with the clouds, because obviously, it's penetrating through the clouds. I was always a bit confused about this. That makes a lot of sense. Very good. What about vegetation on the ground? Could that be an issue if you're taking an image every so often and you do this over a longer time span? There could be seasonal changes or things like that. Is that a problem or?
Yes, it is a problem.
Oh, I see.
So it doesn't work everywhere. It doesn't work when there is dense vegetation. So the reason is the satellite, the wave comes down and it gets scattered back from the ground.
Okay.
And then the next time, so when the scattering characteristics have changed, then the signal is not coherent. And that is what is happening if the signal is scattered back from trees, for example, because of the wind, the trees move. But if there's not too much trees, if there's a little bit of trees, then enough of the signal goes through the trees to the ground. And if there's no trees, then it works very, very well. But if you plow your field, then it's going to be, it's not going to work because the surface has changed.
Okay. So you're working in various parts of the world, but amongst others in Indonesia. And there's quite some dense vegetation in places. Is this a problem for some of the volcano work you're doing there?
It works surprisingly good. So on the island of Java, there's so many people living. Then you have villages and you have streets or some human-made structures, and they don't change. So even if you have a house and there's fields around it, then you're getting you have something permanent from the house.
You have a reference point for kind of calibration, I guess. Yeah.
Yeah. Well, the roof of the house, if it's a roof, or it doesn't change, so there's enough signal scattered back from this building that it still works in most cases. Well, and then it depends, of course, how much time passes by between different acquisitions. So with the old satellites, we got an image only every 35 days or something like that, but and that was not enough, then the ground really changed too much. But now with the new satellite, the new European satellite, the Sentinel-1 satellites, we're getting data, an image every 6 or 12 days, and most of the ground in Indonesia in the populated area stays coherent. Yeah.
That's very good. That's very good. And you published a few papers over the last little while, and I think one of the key findings was that several of the Indonesian volcanoes have rather shallow level magmatic systems, magma chambers in the traditional sense, or reservoirs.
Yes.
And they cause inflation and deflation, or did I misunderstand that?
Yeah, well, that's exactly correct what you said. So what we can measure is if the magma comes closer to the surface, accumulates in the magma chamber, and then of course you're getting an inflation of the ground. And now what happens in Indonesia is that inflation what we observe at the ground, it's relatively localized. And to do that, you really need to have a relatively shallow magma chamber.
Yeah.
In other parts of the world, you have big inflation areas over 10 kilometers or something like that, which is due to a source at greater depths. But in Indonesia, for those volcanoes we have looked, it's more localized and shallow source.
That's very interesting from my personal perspective, because some of the petrological work we did, we do find that quite a number of these Indonesian arc-type volcanoes seem to have a petrological record for shallow magma storage as well, which is consistent with your findings. So I personally thought it was really eye-opening to see complementary methods that are independent to show or point us towards the same direction. You have some information on your laptop here. Should we perhaps have a look at this?
Sure.
Let's see whether I can get the camera over here.
Yeah, so these satellite imagers, they come in, lots of them every day, and we are going towards processing them automatically and obtaining time series for a number of volcanoes. And this, for example, is for Agung volcano, which had quite a crisis a couple of years ago. Last year, we can see here, you can click on each of those pixels and then you're getting the ground deformation. So there was a little bit of uplift and then it stayed more or less constant, but this is actually not a very good example what I'm showing you here. Yes, for this, here it went down and after that it went up again.
Interesting. Okay. So Agung has been very active recently, hasn't it? And you have been monitoring it with your method, I guess. And can you offer any predictions for Agung in the next little while in the future?
It's going to erupt again.
Oh, that's a good one. So
I'm not going to tell you when, I know it, but I'm not going to tell you.
That's great. Well, Falk, this has been very enlightening. Thank you very much for your input and your willingness to talk with me about this. I hope the students will like that too. And well, I believe you when you say that Agung will erupt again. Thank you, Falk.
Okay.
Bye-bye.